So am I audible?
Yes, sir.
Yes, sir.
Now everybody joined, right?
Yes, sir.
Okay. So those who joined now, because that was my mistake actually. In mobile, I was in another ID, Gmail ID. Here I'm in another Gmail ID. So that was my mistake. Anyway, so those who joined now, we were just we were discussing how to find out the wavelength of a monochromatic light using this Newton-Singh experiment. So what we'll do here, we'll generate a Newton-Singh pattern using that monochromatic light source, maybe sodium or any monochromatic light source. After generating that, what we'll do, we'll measure the diameter of any particular order, nth order Newton-Singh. That diameter will be equal to dn square, nth order dark ring. Okay, dn square will be equal to 4n lambda r. Okay, and then what we'll do, we'll measure the diameter of say fifth order n plus fifth order darkening, and the diameter of that n plus fifth order darkening will be equal to dn plus p square equal to 4 into n plus p lambda r. Okay, now this n can be any number and p can be any number. If n is 5, p is 7, then this is the diameter of fifth order darkening. This is the diameter of 12th order darkening or 10th order darkening, like that. Okay, now, what will have to do? You have to subtract this dn square from dn plus p square. If I do the subtract, then this will be equal to 4 into n plus p lambda r minus 4n lambda r. Okay. So this 4n lambda r and 4n lambda r will be cancelled with each other, and remaining 4p lambda r will be there. And from that, we can find out the lambda according to this formula. Lambda will be equal to dn plus p square minus dn square divided by 4pr. Now, what are the things measurable here? The things which we are going to measure here is the diameter of n plus p order darkening and diameter of nth order darkening. After that, we'll divide with 4p and r, where r is the radius of curvature, p is a number, and 4 is a constant. 4 is also a number. So in that experiment, what we have to do, you have to measure the fifth order suppose darkening and 10th order darkening. Then you have to subtract that to find out the value of wavelength. Okay. Now the general procedure to do this experiment is not to find the two diameter of two darkening only. What we do, we measure the diameter of all successive dark rings. Okay, if you measure the diameter of all successive dark rings and plot a graph between dn square with the order of the ring, if you suppose first order, second order, third order, you just measure the dark ring diameter of all dark rings and plotted the square of those diameters along with the order, then you will get a straight line. Okay, you will get a straight line which y-axis will be dn square and whose x-axis will be like n, order of the ring. Now the slope of that straight line will be equal to dn plus p square minus dn square divided by p. Okay, because here it is n, this is n plus p, so x-axis will be n plus p minus, so denominator in the slope will be n plus p minus n, which is going to give you p, and numerator will be dn plus p square minus dn square. So once you get the slope of this plot, then divide that slope with the 4r, where r is the radius of curvature of the plano convex lens. Okay, so if you do that, you will get the wavelength of that monochromatic light. Now this is more precise way of calculating the monochromatic light source, wavelength of monochromatic light source, because here, if at all any mistake will be there while measuring the diameter of any particular dark ring, that mistake will be taken care of. Suppose while measuring you got diameter, one diameter square here and one diameter square here, then what will, and one diameter square on this line, like this, 2 3. So any mistake will be taken care of. If you are not doing this method, if you are not following this method, and you are using these two diameter to find out the uh, wavelength of monochromatic light, then you will get some error in your measurement. Okay, so in order to avoid any such manual error in the measurement, this is the more accurate procedure to do to find out the, and in any any experiment we used to follow this procedure. Do lot of measurement, take a statistical value, statistical average, means take a slope of that, then we find out the unknown parameter. This is the standard procedure we follow in experiment during in physics or any experiment. Okay, To minimize the error, we follow a statistical procedure. Okay, so this is one of the application of Newton's experiment to find out the wavelength of monochromatic light source or non-monochromatic light source. Okay, the next experiment is to find out, or next application is to find out the refractive index of an unknown liquid. Okay, suppose there is a liquid whose refractive index you want to know, but you do not know the refractive index from using any other method. You can use this Newton's experiment to find out the refractive index of that liquid. Let's see how. Now, to find out the refractive index of a liquid, you have to do this experiment twice in the sense, first you generate a thin film of air. Okay, how to generate a thin film of air? Just simply place the planar convex lens over the glass plate. Then whatever film you will get in the gap of these two convex side and plane side, that film will be of air film. Okay, that film will be called as a air film. Okay, that is consisting of air. Now, once you have generated a Newton sync pattern using air as a film in between this plano-convex lens and glass plate, then do this measurement. What is this measurement? Dn plus p square minus dn square for air, that will be equal to 4p lambda r. Okay, that's what we just found out. Okay, dn plus p square minus dn square of air equals to 4p lambda r. What measurement you have to do? You have to measure the n plus pth order dark ring, the diameter of n plus pth order dark ring, and diameter of nth order dark ring. Okay, so that two measurement you have to do. Now, after doing this measurement, you do one thing: take few drops of that liquid. Few means 1 to 2 drops of that liquid, and put those two drops on the plain glass plate. After putting those two drops of liquid, place the place the plano convex lens over there. Now, once you do that, whatever gap is there between the plano convex lens and the glass plate, that gap will be filled up with that liquid, unknown liquid, for which you are going to find out the refractive index. Okay. Now prepared, the film prepared, using which you are going to generate a Newton sync pattern. That film will be of that liquid. Okay, that unknown liquid. Now, once you do that, generate again the Newton sync pattern and do the same measurement dn plus p square minus dn square, and that will be equal to 4p lambda r divided by mu, where mu is the refractive index of the liquid. Okay, so the Newton thing, which is being generated by placing the liquid in between this convex lens and plain glass plate, for that Newton thing, if you measure the dn plus p square minus dn square, then that will be equal to 4p lambda r divided by mu. Now you divide this equation by this equation. If I divide this equation by this equation, then what will get? Dn plus p square minus dn square divided of air divided by dn plus p square minus dn square of liquid is going to give you the refractive index of that liquid. Okay, so to find out the refractive index of any unknown liquid, you have to do the experiment once with air as the medium, or air is the thin film, and once you have to do the Newton sync experiment with liquid as the thin film or as the medium, then you have to divide them. Okay, so so you have to do two measurements: dn plus p square and dn square for air, dn plus p square, same order must be same. If orders are different, then this p number will be different and you won't be able to find out refractive index. You can find out, but another number is going to come. See, so seventh order minus fifth order of the air divided by seventh order minus fifth order of the liquid, then the division of those two is going to give you the refractive index of the unknown liquid. Okay, so you guys understood the two applications, important applications of Newton's experiment.
Yes, sir.
Yes, sir.
So let's move to another interference experiment, which is called Fresnel biprism experiment. Okay, so this is a method, or this is an experimental demonstration for interference, where we are obtaining the two coherent sources by the method of division of wavefront. Okay, so this is called division of this is the method where we generate two sources by the method of division of wavefront. Okay, how we do that? In this case, we take A biprism. A biprism is nothing but an instrument or a device where two prisms are joined together base to base. Okay, if you are taking two prisms and joining them base to base, whatever structure you will be getting, that structure is called a biprism. Okay, now the acute angle of the biprism are very small, like 0.5 degree each. Okay, acute angle means this is a prism and this is a prism, and the acute angle of these two prisms are very small. Okay, these are acute angles and they are around 0.5 degree, whereas the obtuse angle, this angle after joining this angle and this angle, these are 179 degree each. Okay, so and such a structure or such a device is called a biprism. Now, what will happen if we will use a light source in front of these two prisms? Now, this prism, the first prism, will try to deviate this light beam coming from this source, first source. Okay, how it will deviate? This will first light will come here, after incidenting here, that will be refracted little bit, then that will incident on the other surface, then that will be refracted again. Okay, so this prism will deviate the path of the light beam in this manner. First, there will be a refraction from denser to rarer to denser, then another refraction, then it will deviate in this way. So it can be imagined that it can be viewed as that, as if the light beam is coming from another point here. Okay, light beam is coming from another point here. So we can assume that the light beam, after getting deviated from the prism, can be assumed to be coming from another source S1, and that's called a virtual image of the source S, and that is a virtual source S1. Okay, similar thing will happen to this source by this another prism, the other prism also. So by using this kind of structure, you can divide, or you can generate two virtual images of this single source S as S1 and S2, and these two virtual images of the source can be treated as two virtual sources which are coherent to each other. Then obviously the phase difference will be same, as long as the material, the cut angle, the angles, everything are same for these two prisms. As long as those things are happening, then these two sources will emit, or can be treated as emitting lights which are coherent to each other. So these two can be treated as two coherent sources generated from the single source S by using two prisms. Okay, the only condition is that every aspects of these two prisms, like your material, glass material, refractive index, the angles, every aspect of these two prisms must be same. And if that is so, then these two sources can be treated as coherent sources, virtual coherent sources. That's how we are going to generate two coherent sources. Now, uh, yeah. Now the acute angle of the prism are so small that if I give you the Fresnel biprism on your hand, you won't be able to recognize that as a prism. That will almost feel like a plain glass plate. Okay, the acute angle are so small and the obtuse angle is so large that the this base angle will be so large that will almost feel like a glass plate. And using that kind of device, you can generate two sources, virtual sources, which are coherent to each other. Now, once you generate two coherent sources using this single source S and this biprism ABC, now those two coherent sources can be assumed, or can be expanded, or can be treated uh, to make the interference pattern over a screen at a certain distance from this biprism. Okay, so there is a overlapping area between these two beams. One is beam coming from S1 like this, and one is beam coming from S2, and there is a overlapping area here, and in this overlapping area they will interfere. Okay, and depending upon the phase difference between the two beams, they will either interfere constructively or destructively, and you will get a alternate bright and dark fringe pattern. Okay, what is the difference between the Newton's fringe pattern and this fringe pattern? This fringe pattern is almost equal, or this fringe pattern is completely equivalent to the fringe pattern you are obtaining using Young's double slit experiment. Okay, so these two sources, virtual sources S1 and S2, can be treated as two slits of or two slits similar to that of Young's double slit experiment. Okay, so whatever mathematics, whatever physics that you were using to describe the Young's double slit experiment, the same thing can be done here to describe the fringe pattern obtained using this Fresnel biprism experiment. Okay, that means the first conclusion is that, or first inference from the Young's double slit experiment was that the width of the fringe is same everywhere, right? So it is unlike your Newton's experiment, where the width of the fringe is decreasing or along with the order of the fringes. Here the width of the fringes is same everywhere, and the value of that fringe, value of the width of that fringe is equal to beta equals to lambda d divided by d. What is d? D is the distance from this virtual sources to the screen, and lambda is the wavelength of light, and d is the distance between these two virtual sources. Small d is the distance between these two virtual sources. Lambda is the wavelength, and capital D is the distance from this virtual source to this screen. This is capital D. Okay, so if you know all these things, all these three things, you can find out, or you can find out the width of the fringe pattern. Okay, and that width is going to remain same. Width means the distance between the bright fringe to dark fringe, the distance between the two consecutive dark fringe or two consecutive bright fringe. That's called the width of the fringe pattern. That width can be written as beta equals to lambda divided by d, which is similar to that of Young's double slit experiment. Okay, now this is an experimental setup for this. Here it is the biprism. This is the biprism. Okay, here it is the biprism, and this biprism is facing a slit, facing a light source, which is getting obtained from a extended source like sodium lamp. In front of a sodium lamp there is a slit. Okay, so from that slit you are obtaining your main source S. Okay, now using this biprism you are obtaining two virtual sources along with this, just above and below this main source. Those virtual sources are supposed to generate an interference pattern. That interference pattern can be observed by using this microscope. There is a microscope here over the bench, this optical bench, and that microscope can be used to visualize that fringe pattern. Okay, now, uh, yes, the only condition in order to the only condition to see the fringe pattern is that the slit, the Fresnel biprism, and the microscope, they all must be on a same plane. Okay, if the plane of biprism or slit or microscope are different, then you won't be able to see the fringe pattern. They must be on the same horizontal line. If not, then you won't be able to see the fringe pattern as shown in this figure. As shown in this figure, all are in the same plane. Okay, so you need to take care of that thing. First of all, by using some leveling method, you have to level the entire optical bench. After leveling that, only you can see the fringe pattern, otherwise you can't see. Okay, now using this experiment also, you can find out the wavelength of a unknown light source. What you have to do, you have to generate a fringe pattern using that unknown light source. Then you have to measure the fringe width using that microscope. There is a microscope over the optical bench that can be moved in a horizontal manner and vertical manner as well. And using that, you can find out the fringe width beta, and you can find out the distance between two virtual sources, and you can measure the distance between the screen and source, and that is going to give you the value of the wavelength of unknown light source. Okay, so what is the procedure to do that? Now you have to keep the slit, biprism, and microscope on the same height. That means on the same line. Without that, you won't be able to see the fringe pattern. There will be some error. uh, then after that, you observe the fringe from certain region. Suppose this is E region, overlapping region E, this is overlapping region F. Then from E to F you count the number of fringes. Okay, you count the number of fringes from E to F. And if the distance, if the distance from E to F is xn minus x0, the distance between E to F is xn minus x0 over the microscope, then the fringe width can be written as beta equals to xn minus x0 divided by n. Okay, so like this you can find out the fringe width, measure the total number of fringes that are getting generated from a certain distance xn to x0, then divide that distance xn minus x0 by the total number of fringes, that is going to give you the width of a single fringe. Okay, so that is going to give you the value of beta. You can measure the value of d also by using a scale on the setup itself. On the setup itself there is a scale, and from that scale you can find out the distance from the source to that screen. Screen is the microscope, and source is this slit. And obviously the distance from the virtual sources will be same as the distance from the main source. So that is going to give you d. Then another thing you need to find out is the distance between the two sources. Okay, two virtual sources. To find out the distance between two virtual sources, you have to keep a convex lens in between the. Here it is a convex lens. You have to keep a convex lens in between the biprism and this microscope. First, what will have to be? What will have to do? You have to move this convex lens towards this biprism. At a certain point, you will see that when the object when the magnification can be written as the object distance divided by image distance. At certain point you will see that these two sources, S1 two virtual sources, they are quite well focused. At certain point you will be able to see them separately, in a focused way. The focus will be great, or the focus will be maximum at a certain point. The focus of observing these two virtual sources will be maximum at a certain point when you will move this convex lens towards this biprism. Now treat that distance as d1. Okay. Now again, if you will move the convex lens away from the biprism, at a certain point you will find that again the focus is maximum. Okay, you need to find out these two focus points, and that distance can be treated as d2. Now once you found out d1 and d2, you can find out the distance between two virtual sources by using this method. D equals to d1 minus d2. Obviously d2 will be greater than d1. Okay, so this this you can use this formula d1 d2 of the square root to find out the value, or to find out the distance between the virtual sources. So you found all these three things using this experiment. One is capital D, one is small d, and one is beta fringes. Now by using these three you can find out the wavelength of the unknown light source, that is sodium, over here in this experiment. This experiment we used to do in our lab. Neutral Singh experiment and this Fresnel biopsy we used to do in our lab. So this is the way to find out the wavelength of non-light source by using this Fresnel biopsy case. Okay, so I'll upload. Okay, let me show a little bit what are these small distance d1 and d2. Now this is the bioprism in your experimental arrangement, and this distance is small d. This distance is the distance between two virtual sources. This is the bioprism. This is the position of the convex lens. Okay, now when you will move the convex lens towards the bioprism, at a certain point, you will be able to focus these two virtual sources nicely. Okay, that point that point is going to give you the going to give you the distance d1. Okay, that point is going to give you the distance d1. Now d1 means, how to find d1? Once you place the convex lens here, now take the distance from one virtual source to another virtual source. That is going to give you the value d1. Okay, now move the convex lens towards this, toward or away from the biprism while looking at this eyepiece. Now Now at a certain point you will be able to focus these two virtual sources S1 and S2, and once you focus that, measure this distance from here, from here to here, okay, using this my eyepiece, this microscope, okay. This distance is going to be called as d2. The other distance is going to be called as d2. Now for the first case also, this is u by v, the object distance divided by image distance is not nothing but going to give you the magnification. The second case also, this is going to give you u by v, and when you divide that, you are going to get the value of d, which is nothing but d1 into d2 of the root over. Or you can find out the value of d, you can find out the value of d by using any one position also. But in order to make the measurement more accurate, you can use the both the position, and you can use the formula d1 d2 of the square root. Or else you can find out, you can measure this object distance u, you can measure this of the image distance v, you can measure this d1, this distance between this magnified image this distance between s1 and s2 in the magnified form. Then d divided by d1 is going to give you u divided by v, okay. So if you know u, if you know v, if you know d1, then you can find out d from there. Or else you can use both of them to find out the value of d using this formula. Both can be done, okay. So this is the way to find out the value of d, the distance between the two virtual sources. So this is all about this Fresnel biprism experiment. This is quite similar to your Young's double slit experiment. So only thing is that in case of Young's double slit experiment, you are able to find out the small d, the distance between two slits, directly by using a scale. Here you have to use a optical method to find out the distance between two virtual sources S1 and S2. That is the only difference. And apart from that, everything are same. The mathematics, the physics, everything are going to be same. Okay. So any doubt?
No, sir.
Okay. So Sir, can you please send the attendance? So this was all about your syllabus in for the MCQ1. Your in your MCQ1 questions are going to come from this interference, Newton's ring, and Fresnel biprism. There will be no diffraction. Your exam questions are going to come from these three only. Okay. Can you who is here? Can you send me the attendance?
Yes, sir.
Yes, sir.
Okay, Amisha, please send the attendance. Are you taking screenshot or you are just noting down who is absent? Anything is fine for me.
Yes, sir. I guess everyone is present